Now, basically in inverse design, we specify the vortex distribution at the leading and trailing edges of the blade, and this in turn controls the Euler work in case of the impeller or the inviscid flow turning in case of the diffuser. So in the third study, the impeller work profile at the trailing edge is varied from the original free vortex distribution, and in fact, this can also be done pretty quickly in TD1. So this time in the blade loading section, you can change the distribution to linear mean. And then now you can increase the shroud work like this, and this will reduce the hub work, but the mean work will be preserved, which is what you want. And then just as before, you can compare the changes in geometry and pressure distribution in these 3D and 2D plots respectively. So two configurations are generated in this way. In the first one, the specific work decreases from the hub to shroud, whereas in the second, it increases from the hub to shroud. And again, a close correlation can be seen with both TD1 and CFD plots confirming an increasing in the hub loading in the first case and an increase in the shroud loading in the second case. But these changes again are mostly seen towards the rear of the impeller, and so there isn't much change in the pressure valley. And in terms of other results, we can see that the work distribution from CFD, which is the solid lines, very closely follows what were specified in TD1 or the dotted lines for both configurations. And another interesting result is both configurations actually presented a drop in efficiency. And the reason is that the hub is characterized by a considerably smaller radius than the shroud section. And so increasing the hub work in either the impeller or diffuser requires a much larger flow turning there with a consequent increase in the boundary layer losses.